Today, we're going to get into the chemical origin story of one of the most common medicines on the entire planet. Yeah, it's a story all about pressure, temperature, and this brilliant 19th century discovery called Kolbe's reaction. I mean, seriously, think about it for a second. Every time you see a bottle of aspirin, you're looking at the final result of this really fascinating, really powerful chemical process. But how does that all get started? Where does aspirin actually come from? Well, the answer might surprise you. It's not found in a plant, at least not directly anymore. Nope, it's found in an industrial reaction, one that's a total cornerstone of organic chemistry and, you know it, a big favorite on exams. Okay, let's get into it. So, we're talking about the Kolbe reaction, or as you'll also see it called, the Kolbe-Schmidt reaction. This is the industrial powerhouse that really kicks off the entire aspirin manufacturing process. Okay, let's break that down. What is this thing exactly? Well, in pretty simple terms, it's a carboxylation reaction. That's just a fancy way of saying its whole job is to add a specific group of atoms, a carboxyl group, onto another molecule. In this case, it skillfully attaches that group to phenol, and the whole point of this really elegant move is to produce one critical compound, salicylic acid. And like any good recipe, this one needs very specific ingredients and really precise conditions. If you get any part of it wrong, believe me, the whole thing just fails. The starting lineup is actually pretty straightforward. First, you start with phenol. Then you bring in sodium hydroxide, which is a strong base, and you follow that up with simple carbon dioxide. And then at the very end, you need just a splash of acid to finish the job. But, and this is a big but, just mixing these things together in a beaker isn't going to do a thing. The real magic, and the industrial challenge, comes from creating the absolute perfect environment for them to react. First off, you need heat. And we're talking about 125 degrees Celsius. This gives the molecules the energy they need to get moving and get ready to react. And here's the other big one, you also need some serious pressure, about 6 to 7 times the normal atmospheric pressure you're feeling right now. This is what literally forces the carbon dioxide, which is a gas, to get in there and interact with the other ingredients. So you mix your ingredients, you apply all that heat and pressure, and what do you get? You get the star of the show, ortho-hydroxybenzoic acid. Now that is a mouthful, so we all know it by its much more common name, salicylic acid. And this is the direct precursor to aspirin. Okay, so we know the what, but what about the how? How does this actually happen on a molecular level? Let's peel back the layers and take a look at the step-by-step mechanism that makes this whole thing tick. It's actually a really elegant 3-step dance. So first, the sodium hydroxide comes in and plucks a hydrogen right off the phenol. This creates something called a phenoxide ion, and this is the crucial step that basically supercharges the molecule. Second, that now activated ring is ready for action and it attacks the carbon dioxide. And finally, a little bit of acid is added to neutralize everything and give us our stable final product, salicylic acid. That first step, creating the phenoxide ion, is the absolute key to this entire reaction. Think of it like this. Phenol on its own is just too passive. It's not interested in reacting with something like CO2. But by turning it into an ion, the ring becomes super electron-rich and activated. It makes it aggressive enough to go out, seek, and bond with that carbon dioxide. But why does that new group attach right next door to the existing OH group? In chemistry, we call that the ortho position. Well, it's all about stability. When it's in this position, the two groups can form an internal hydrogen bond. It's like a little chemical handshake that holds the molecule together more tightly. And that arrangement makes it the most favorable, most stable outcome. Now, while aspirin is definitely its most famous child, the salicylic acid that we get from Kolbe's reaction has a much, much wider legacy. It's a really versatile chemical building block that's used all over different industries. So the crucial point here is that this reaction is not a one-trick pony. Not at all. Yes, it's the essential precursor for aspirin, but that exact same salicylic acid is also used in making vibrant dyes, formulating scents for perfumes, and as a general starting point for a whole family of other useful chemicals. Okay, now for anyone out there studying chemistry, you're gonna want to listen up for a second. There is a classic exam question that is designed to trip you up, and it involves another reaction with Kolbe's name on it. The difference is really stark when you look at them side by side. Our reaction, the Kolbe-Schmidt reaction, starts with phenol and makes salicylic acid. Simple. Kolbe electrolysis, on the other hand, is a completely different beast. It starts with a carboxylic acid salt, it uses electricity, and it creates a hydrocarbon. So same name, but a totally different process and a totally different outcome. Don't fall for that trap. All right, let's bring it all together. What are the absolute key takeaways from all this? Number 1, Kolbe's reaction turns phenol into salicylic acid. Number 2, it needs a strong base, CO2, and some serious heat and pressure to get the job done. Number 3, it's the industrial backbone for making aspirin. And finally, remember, the ortho-product is the winner because it's just more stable. So from a simple phenol all the way to the precursor for aspirin, Kolbe's reaction is just a perfect example of incredible chemical ingenuity. It really makes you wonder, what other everyday products that we totally take for granted have a hidden story, a clever bit of chemistry that's just as fascinating?